Hi, I'm Dr. Saroja, retired professor in chemistry. Today I'm going to talk about a very important thermodynamic property, enthalpy. What is enthalpy? Enthalpy is represented by a symbol H, capital H, is the total heat content of a system. It is a state function. It depends only on the state of a system and not on the path followed to attain the system. It is the energy stored in the chemical bonds of a compound. Chemical bonds have characteristic enthalpies that denote the energy required to break them, homolytically called bond dissociation energy, BDE. It is a delta H value and that is positive, and breaking of a bond is always an endothermic process. BDE, bond dissociation energy of CH single bond, is plus 413 kilojoules per mole, and OH bond is plus 467 kilojoules per mole, and O double bond O is plus 495 kilojoules per mole. On the other hand, creating a bond between two atoms must release energy, and delta H should be negative. Making a bond is always an exothermic process. If this were not true and the bond atoms are at a higher energy than they were unbound in the atomic state, such a bond would be unstable because of high energy and it dissociates immediately, as stability is always associated with low energy, and that's why atoms always combine to form molecules because they are attaining a low energy state. Bond formation always releases energy and bond breaking always requires energy. Enthalpy let us see as a composite function. H enthalpy is equal to E internal energy plus P external pressure into volume. H is enthalpy, E is internal energy of the system, P external is a constant external pressure like the atmospheric pressure, and V is the volume of the gas. Delta H change in enthalpy is equal to delta E change in internal energy plus pressure external into delta V change in volume. At constant pressure, the heat flow for any process is equal to the change in internal energy of the system plus the pressure volume work done. P delta V is the pressure volume work done when a gas expands from volume V initial to V final. When a gas expands against an external pressure, work is done by the system and the energy of the system decreases because the gas is spending the energy. Hence, W is given negative sign by convention. When the external pressure does work on the gas contracts and the energy of the system increases. Hence, work is done on the system is always given a positive sign by convention. Let's see what is standard heat of formation. Delta H 0 stands for standard and F is formation. Standard heat of formation is the amount of energy required to make 1 mole of compound from its constituent elements in their standard states, the way the element exists at STP. The convention is to assign delta H0F for elements in standard state as 0. For all elements, delta H0F in standard state is 0. For example, delta H0F for carbon graphite and oxygen gas is 0. Now let's see the formation of carbon dioxide gas. Carbon gas, graphite plus oxygen gas giving carbon dioxide gas. Delta H0F is equal to minus 393.5 kilojoules per mole at standard temperature, that is 298.15 K. It is the standard heat of formation of carbon dioxide gas. Standard temperature is 298.15 Kelvin and the standard pressure is 1 atmosphere. Delta H0F can be positive or negative. When delta H0F is positive, it is endothermic. Heat is required to make 1 mole of a compound from its elements in standard state. Heat of a reaction, let us see. Delta H0R. R stands for heat of a reaction. It is a measure of heat energy absorbed or evolved during a reaction at constant pressure when bonds are broken or formed. When bonds are formed, delta H is always less than 0 and it's an exothermic reaction. Delta H is equal to negative. Energy is required to break the bonds, therefore delta H value is always greater than 0 and it's positive. In a reaction, bonds are broken in the reactants and energy is absorbed. New bonds are formed in the products and energy is released. The difference between the enthalpy of the products and the reactants is the enthalpy of the reaction. Delta HR is equal to sigma H, total heat content of the products minus total heat content of the reactants. Let's see how to calculate heat of a reaction for combustion of methane. There are three methods, and the first method is from standard heats of formation. Delta H0R is always equal to sigma sum total of n number of molecules into delta H0 formation of products minus sum total of all molecules into delta H0 F of reactants. For example, methane gas getting burnt in excess oxygen is called combustion, and that gives carbon dioxide gas plus 2H2O liquid. Delta H0R for this reaction is equal to delta H0 formation of carbon dioxide gas, that is the first product, plus 2 water liquid molecules 2 into delta H0F liquid water, products are over, minus reactants delta H0F for methane gas and 2 oxygen molecules 2 into delta H0F for oxygen gas. Now let's see the heats of formation. Carbon solid plus oxygen gas giving carbon dioxide gas, delta H0 formation is minus 393.5 kilojoules per mole. Let's call this equation 1. Now let's see the heat of formation of H2O liquid. H2 gas plus half oxygen gas giving H2O liquid, delta H0 formation is equal to minus 286 kilojoules per mole. Let's call this equation 2. Now equation 3 is formation of methane gas. Carbon solid plus 2 hydrogen gas giving methane gas, delta H0F is equal to minus 75 kilojoules per mole. This is equation 3. Now let's calculate. Let's see delta H0F of oxygen, because this is elemental oxygen. Delta H0 values for formation are always 0. Now let's calculate delta H0 reaction for this combustion of methane. So we have to first write the delta H values for products. So the first product is carbon dioxide, and carbon dioxide heat of formation is minus 393.5 kilojoules per mole plus 2 water liquid. Water liquid is given by the second equation, so plus 2 into minus 286 kilojoules per mole. So the products are over. Now minus reactants. Methane gas formation is equal to minus 75 kilojoules per mole, plus here we have 2 oxygen molecules, and the delta H0 formation of oxygen, because it is an element, it is 0, and 2 into oxygen, 2 oxygen molecules 2 into 0 is also 0 kilojoules per mole. So what is the answer? When you calculate all this, you will get minus 890.5 kilojoules per mole. This is the heat of reaction of combustion of methane. This is method 1. Now let's see method 2. Calculation of heat of a reaction for the same combustion of methane by the second method, that is from the average bond enthalpies. The very word average shows that bond enthalpies are always average values. Delta H0R is equal to sum total of bond dissociation energies of bonds broken minus sum total of bond dissociation energies of bonds formed. Now let's see what are the bonds broken and what are the bonds formed. Methane undergoing combustion plus 2O2 gas giving carbon dioxide gas plus 2H2O liquid. For this reaction, what are the bonds broken? Delta H0R is equal to sigma sum total of, in methane there are 4 CH bonds, so 4 into CH bonds, plus in oxygen there are 2 O double bond O bonds, so 2 into O double bond O. This is the bonds broken minus bonds formed. These are the bonds formed. The bonds formed are, in CO2 there are 2 C double bond O's, so 2 into C double bond O, plus in water there are, in each water molecule there are 2 OH bonds, and in 2 water molecules there are 4 OH bonds, so 4 into OH. Now for this, let us calculate. The bond dissociation energy values for all these bonds are listed here. Bond dissociation energy of CH is plus 413 kilojoules per mole, and O double bond O is plus 495 kilojoules per mole. C double bond O is plus 799 kilojoules per mole. OH is plus 467 kilojoules per mole. Now let us substitute all these values in this equation. Delta H0R is equal to sigma 4 into CH, that is 4 into CH is plus 413. So 4 into 413 plus 2 oxygen double bonds, that is 2 into plus 495 minus 2 here 2 C double bond O. C double bond O is 799. So 2 into 799 plus 4 OH bonds. 4 into 467. So if we calculate this, we will get a value of minus 824 kilojoules per mole. Now you see the difference. In the first method, we got 890.5 kilojoules per mole for the same combustion of methane. Now in the second method, we got minus 824 kilojoules per mole. The answers are different. The answer in these two methods is different, as the bond energies are always average of many examples of that type of a bond, which are approximations of the strength of the bond. And delta H0R also is an approximation, because we are adding up summation of bond energies which are average. Whereas in the first method, delta H0F in the first method, those are the determined values, experimentally determined values for each individual chemical compound. Therefore, that is an experimentally proven value. So that is the difference between the two methods. Now let's see the last method, that is delta H0R from Hess law of constant heat summation. Dr. German Hess, a Russian chemist, published Hess law in 1840. What is the law? The heat of a reaction delta H0R for any particular reaction is equal to the sum of the heats of reaction for any other set of reactions, which in sum are equivalent to the overall reaction. That means we can take any other set of reactions, but at the end the reactants and the products must be the same. Then in that case, delta H0R of these two reactions are equal. Hydrogen gas, a clean fuel. It is of potential interest globally, and this can be generated by the reaction of carbon in the coal form and water, and it is an endothermic reaction. For example, carbon solid plus 2H2O gas giving carbon dioxide gas plus 2H2 gas, delta H0R is equal to 90.1 kilojoules per mole at 298.15. This is endothermic. So if it is endothermic, for this reaction to take place, where does this energy come from? So we will see this from two other connected reactions, how this energy comes from. Now the first reaction is this carbon dioxide gas formation from carbon solid, this carbon solid plus oxygen gas. It consumes oxygen gas and gives carbon dioxide gas. This delta H0 formation is minus 393.5 kilojoules per mole, and let us call this equation 1. Now we are trying to arrive at this equation from another set of equations. So this is equation 1. Now equation 2 is 2H2 gas plus oxygen gas giving 2H2O gas. This one, 2H2O gas, we are getting from oxygen and hydrogen. Delta H0F for this is minus 483.6 kilojoules per mole. So we are making use of these two equations, and we are trying to see if we can get this equation. Now subtracting equation 2 from equation 1. When you subtract equation 2 from equation 1, this product will go on the reactant side on subtraction, and these reactants will come on the product side. Then we will add these two reactions. Now let us add the two reactions. Carbon solid plus oxygen gas, and this 2H2O from the product side, it will come to the reactant side because we are subtracting 2 from 1. So 2H2O gas gives carbon dioxide gas from the first equation, and these two reactants will become products now because we are subtracting equation 2. So plus 2H2 gas and oxygen gas. Now oxygen is there on both the sides. Oxygen on the reactant side, oxygen on the product side gets cancelled. Now we have arrived at our original equation. See, carbon solid plus 2H2O gas, carbon dioxide gas, 2H2 gas. We have arrived at this equation with the help of these two equations. So that is what is Hess law. If we get equivalent equations, then we can sum up the heats of reactions also. Now here let us subtract the heat of reaction for the second one from the heat of reaction from the first equation. Then we will arrive at delta H0 value for this reaction for the production of hydrogen. So delta H0R is equal to equation 1 minus 393.5 minus of minus, because we are subtracting 2 from 1, minus of, there is already a minus sign here. So minus of minus 483.6, that is giving exactly the same 90.1, which is equivalent to the heat of reaction of the first reaction. So that is how Hess law is proved. So you can get the same equation in terms of the formulae, reactants and products, as well as in terms of the heat of reaction, also from a different set of reactions. Then if both are equal, that means Hess law is proved. So this is the third method of calculation. We can get the value from any other set of reactions. So this is the Hess law of constant heat summation. So thank you so much. Thank you for a patient hearing, and if you like my video, you please subscribe to this, and in the next video I'll come up with another very important thermodynamic property. Thank you so much.